Hello and good time of day, everyone. Welcome to this new MLIR open meeting. And today, Navdeep Katal and Uday Bondugula will present about high-performance GPU Tensor Core code generation for Matmul using MLIR. Uday?
Hi everyone. My name is Uday, and so we are pleased to be presenting this at the MLR Open Design meeting. And this is really a work on automatic code generation for GPUs. And our goals here are to share preliminary results to on some promise on what we think are some promising directions to discuss with the community and encourage collaboration on some of the surrounding infrastructure to MLIR, and also to have all of our work to be upstream, starting with the lower layers. And so this talk is going to be delivered by Navdeep, who was a master's student at the Institute of Science, and he was a research intern at Polyimage Labs as well. And the part of his work was done for his thesis as well as then as for the research internship at Polyimage Labs. So I think let's keep this interactive. Please feel free to ask questions, and we're happy to answer questions, and as long as we're able to finish in time, right? So so Navdeep, it's all yours. Thanks.
Yes. So thank you for the introduction. So the topic of today's talk is like high performance GPU Tensor Core code generation for matrix multiplication using MLIR. So just to start, we'll start off with some motivation, what motivated this work, and So the state-of-the-art high-performance deep learning is primarily driven by hand-tuned libraries. So these libraries are often written by expert programmers and then tuned further using some low-level programming. Effort may need to be repeated for any other similar hardware that may come in the future, or may also be repetitive across different vendors. So what we can try to do is try to make this process more modular, systematic, and automatic to the large extent possible, and by building a correct set of abstractions, transformations, and optimizations to generate the code automatically. And of course, all of this could be made possible using the MLIR compiler infrastructure. Going forward, we would just discuss briefly about GPUs, the general hardware design, about tensor cores, the programming model, and the compilation path that we take to generate matrix multiplication kernels. So GPUs are really highly specialized parallel piece of hardware, which are just basically made up of a bunch of streaming multiprocessors that are grouped together. These streaming multiprocessors are then further partitioned into processing blocks, and each processing block has a characteristic that it has an individual WOP scheduler. So this means that each WOP scheduler can schedule a number of WOPs, and so in the figure shown in the right actually has 4 processing blocks and 4 WOP schedulers. So this really means that 4 WOPs can be running in parallel on the streaming multiprocessor. There will be multiple streaming multiprocessors, and each has some thread block map to it. So in general, there will be a number of thread blocks also running in parallel. Now, these streaming multiprocessors, these processing blocks inside the streaming multiprocessors have a shared L1 data cache that is basically shared among all the processing blocks, while the other resources such as the registers and the load store units, the compute units, and the tensor cores are partitioned uniformly across all of these processing blocks inside the streaming multiprocessor. So on the right side is basically a figure borrowed from the Ampere GA102 white paper showing the streaming multiprocessor. The memory hierarchy can simply be abstracted into a 4-level structure. Starting from the fastest, these are the registers, then there's an L1 cache, which can also be basically partitioned to be a programmer-controlled scratchpad memory known as the shared memory. Then there's the L2 cache, and then there's the slowest global memory, the dynamic memory RAM, which is shared among all the streaming multiprocessors. Coming to the tensor cores, so tensor cores are special units for matrix multiply that were introduced first in the Volta architecture, then present in Turing, and are present in Ampere as well. So basically, they perform a small matrix multiplication of size around 8 cross 8 cross 8 or something like that in a single cycle. So the performance of these tensor cores is really high as compared with the CUDA cores, And originally, when introduced, this tensor core supported only FP16 inputs with two accumulation precisions, that was FP16 and FP32. But really now, more data types are supported, like BF16 and TF32 as well. So this table is just basically a reference as showing the performance of the normal CUDA cores and the tensor cores. So looking at this Ampere thing, the RTX 3090 on FP16 accumulate, the performance is roughly 4 times or something like that for the tensor cores versus the CUDA cores. And the similar trend follows on the Turing RTX 2080 Ti as well. Learning that these tensor cores are a really important piece of hardware that we have, we need to also discuss now what are the different ways to program these tensor cores. So tensor cores can basically be harnessed by three approaches. One is out of the box. You can use a library which is vendor provided, like QBLAS or QDNN, and they're usually the fastest. But the downside with these libraries are that they have like limited support for operator fusion. QBLAS LT is catching up. They have provided some support for fused kernels for ReLU and bias addition. But really, if you need something else, like, you will have to wait for someone at NVIDIA to implement the kernel for that and provide them in the library. The second approach to program the tensor cores is using the WMM API, which stands for Warp Matrix Multiply Accumulate API. This is provided by NVIDIA and basically provides utility functions for loading and storing matrix fragments from shared memory into the registers and then storing back to the shared memory or global memory from the registers. Now, the downside to this is, like, you cannot totally avoid bank conflicts, as we'll see later and discuss in more detail. The bank conflicts cannot be totally avoided when we use this approach. And the upsides, there are two upsides. Fused kernels can be implemented by the programmer himself now, and the lowering to the actual target instructions is now offloaded to NVIDIA's compiler or the assembler, which will convert these things to the real PTX instructions. The last approach here is that the programmer himself uses inline assembly and to use the PTX instruction called MMA sync to program these tensor cores. Now, there's some downside. You don't get the utility functions, all the utility functions that you got with WMM API to program the tensor cores. But a really upside for this is, like, you get almost a good control over bank conflicts by using switchable layouts in shared memory. And basically, the bank conflicts can be totally avoided. This provides equivalent support for fusion as well. Moving forward, we'll briefly discuss about the programming model for GPUs. So in GPUs, basically, the basic execution entity is a thread. A thread is clubbed into a group of 32, which is called a WOP. A WOP executes in lockstep manner and is basically chosen by a WOP scheduler to be scheduled to run on the processing unit. WOPs are further grouped into thread blocks, and each thread block is bound to a single SM. Thread block cannot change an SM during its lifetime and runs completely on a single streaming multiprocessor and releases all the resources when it's done. Registers belong to a thread and are private to it. No other thread can read a single thread's data. If threads want to communicate, threads in a thread block can communicate using the shared memory, while threads from different thread block need to communicate using the global memory. Synchronizations are present at the thread block level and the WOP level and can be basically used by the programmer according to their needs. Last thing we'll be discussing about GPUs is the compilation part that we take when doing code generation from MLIR. So MLIR basically relies on the LLVM infrastructure to generate the actual code. So once you are done applying all the optimizations and transformations on MLIR, you convert your MLIR to LLVM-IR. Now, this LLVM-IR is given to the NVPTX backend in LLVM, which emits the PTX code. This PTX code is again given to NVIDIA's assembler that converts into SAS, and subsequently you get a CUDA binary to execute it on the GPU. Having had the background for GPUs, we can start discussing about matrix-matrix multiplication, its importance, and the general recipe for high-performant implementation of matrix-matrix multiplication on GPUs. So Matmul in the general form is represented by this equation: D is equal to alpha times AB plus beta times C. Alpha and beta are scalars, and the dimensions of A, B, and C matrices are m cross k cross n, and m cross n. D also has the dimensions as m cross n. Matrix multiplication has order of n cube computation on order of n squared data. So basically, there's roughly order of n reuse for each data element present. It's at the heart of many deep learning models, such as BERT, which our experiments showed that around 50 or 50 to 55% of time in BERT is basically spent in doing matrix multiplication. And the most fastest implementations of Matmul come from the vendor libraries like QBLAS. Other works like Cutlass are coming up, and basically they also achieve performance that's comparable to QBLAS and maybe even better in some cases, while providing different abstractions and different ways to program the tensor cores and write matrix multiplication codes. Cutlass also highlights the general recipe for efficient matrix multiplication on GPUs. So, which is shown in this figure. So basically, you start off with all your input matrices in the global memory. You tile it and assign these tiles to individual thread blocks. Each thread block will move its operand tiles into shared memory. After moving them to shared memory, this thread block tile will again be partitioned among two warp tiles. And then again, this warp will be responsible for only calculating a certain part of the output. A warp will move its operands from shared memory into the registers. Do the CUDA cores or the tensor cores will do the computation here. Now, it may so happen that the results produced by the tensor cores may not be in the output that's expected, may not be in the format that is expected in the output tile. These results can still be stored to the global memory in the same way, but the performance may be suboptimal. So an extra step that has to be done is you basically write the results into shared memory, and then you write it in the most efficient way back to the global memory. And here, once you store it back to the shared memory, you can load it again to do some point-wise operations such as scaling, multiplication with beta, or addition, or something like that, and store the result back to global memory in the most efficient way possible. Having discussed about matrix multiplication, apart from the things mentioned in the previous slide, there are some other performance guidelines that one must follow to generate the most efficient code. Two-level tiling was discussed previously. This parallelization of independent tasks. Each output tile is calculated independently by a thread block. Inside the thread block, each part of the output tile is again calculated independently by the warps in the thread block. What more, you need to ensure that the accesses to the memories, global memory and shared memory in particular, are efficient. Global memory requires the accesses to be coalesced in order to achieve the exploit the whole bandwidth that's available. And the shared memory has some things called bank conflict, which are really needed to reduce to be very less in order to get good performance. You also need to overlap the memory transfers with compute. This is basically hiding the latency of global memory loads. When you try to load things from global memory, you want that some compute should be happening in parallel when this is happening. The last thing is, like, you may also want to use vectorized memory accesses wherever it is possible. Now, having discussed all of these things, we will move on to the pipeline that we have put together in MLIR for this matrix multiplication code generation. The pipeline basically encodes all of the optimizations that have been said before, and yeah, we'll just move forward. So this is the whole design of the pipeline. It's basically a collection of MLIR passes, and basically it assumes a high-level IR to give the input, like cleanalg or something, to give the input to start with the pipeline. Once you have the input, we assume it to be a like a affine loop nest of 3 loops, which represent the matrix multiplication. We start off by doing the 2-level tiling. After tiling, we try to create and place the shared memory buffers. These shared memory buffers are then padded. After padding, we need to generate WMA tensor core ops. Remember that the affine loop nest we had scalar operations. Now these scalar operations are mapped to this WMA operations on tensor cores. Then you need to permute, unroll, jam the loops in a specific order that are necessary for performance. Moving further, you need to do a specific transformation, basically for the global memory load latency hiding, which essentially translates to a pipelined main K loop of this matrix multiplication kernel. And you can move on to insert some synchronization barriers and you can choose to do the global to shared copy vectorization followed by a normalization of these copy loops. Now, doing normalization at this point enables some further canonicalizations that we observed in the code generated. Plus, it has another benefit that it encodes the number of total elements to be copied as the loop upper bound, which is essentially used later in the pipeline when these copy loops are going to be mapped to a thread block. You detect the parallel loops next and convert these affine dot first to affine dot parallels, and you try to collapse any perfectly nested affine dot first into a single affine dot parallel. So this is just basically a utility step to enable mapping of these loops to the compute hierarchy easily. After collapsing these loops, you can basically convert to the SCF dialect, and you can try to map these loops to the GPU compute hierarchy. You try to map the outermost loops to thread blocks, the next loops to warps, and yeah, that's it. You need to move, just go till the level of so the outermost loops are to be converted into the gp.launch op, and basically they are mapped to the thread blocks. And the next two steps, the unroll global to shared copy and then decoupling of load and store, are basically completing the latency hiding stuff that we had earlier. After doing all these optimizations, you load down to STD dialect and then LLVM dialect, and again this goes through the LLVM and PTX backend, and you get the queuing to execute at the end. The whole pipeline design of the pipeline basically started with the design of the WMMA ops, which were absent from MLIR in the first place. So these WMMA ops are basically one-to-one mapping with the WMMA intrinsics, which were present in the NVPTX backend, which are in turn one-to-one mapped with the WMMA functions that are provided by the WMMA API from NVIDIA. So these three ops, GPU.subgroup MMA load matrix, store matrix, and MMA compute were added, and these were supported by an opaque type GPU.MMA matrix, which was added to support the operations that these ops provide. So this is an example usage of these operations. First, you use the gp.subgroup MMA load matrix. It takes as operand a memref and indices into the memref from where you want to load the matrices. So here it's basically a 1024 cross 1024 matrix, and a small 16 cross 16 matrix is being loaded by this op. You can use the subgroup MMA compute op to perform the actual matrix multiplication. The result produced by this op can be stored back to the global memory or shared memory using GPU subgroup MMA store matrix op. Yeah.
So there is a question on the chat. I'm going to read it out loud for everyone. So Prashant asked, I wonder if the layout of matrices in shared memory are different to things that are required by Tensor cores. And if so, how do you handle that in your overall flow?
I didn't quite get the question.
And I think the question is whether we're using different layouts.
Okay.
For example, affine maps. So I think maybe I can answer this quickly. So we use just a default row major identity layout for all matrices and even the intermediate buffers that sit in the shared memory. Basically, the WMMA ops are going to load the 16 cross 16 tiles from within these buffers, right? So that's what is going to happen. And so we don't use any non-identity or different kind of tiled layouts. Yeah.
I see. So that.
Go ahead,
but so I think so my thought process is also that would this lead to the suboptimal performance going in those layouts? Maybe I'll wait for the experiment results before going forward.
Okay, yes, it's we can discuss more when we get to the experimental results.
Yeah.
Okay. Yes. So moving forward, we will take this piece of IR as the starting point for our code generation pipeline, and we'll just see where this leads us. So this sort of IR, when mapped to the tensor cores and doing everything, but each optimization is turned off at this point. This gives us around 3.9 teraflops of performance. Now, this is a mixed precision matrix multiplication on an Ampere RTX 3090 Ti, where the peak is 71 teraflops and QBLAS achieved 68.26 teraflops. The matrix size is 8192 cross 8192 cross 8192. It's a square matrix, and the problem size is basically square. Yeah, so starting off at 3.9 teraflops. As discussed earlier, two-level tiling is essential. Matrix multiplication involves redundant accesses to the slower memory, the global memory. So basically, you tile your computation, move the tiles to shared memory, tile it once again, and move the relevant tiles to registers, and parallelize at the same point. So tiles in parallel will be computed by thread blocks and computed in parallel by WOPs. In this way, you can basically eliminate the redundant accesses to shared memory and the global memory at the same time. So multi-level tiling was done in MLIR using the affine loop tile utility, and followed by the affine data copy generate to generate the copy lists for global to shared data copy. The missing parts in these utilities were added and added accordingly. Yeah. So we'll just see what this gives us. So doing the shared memory tiling improved the performance like 2.5 times, taking us to 920 teraflops, and doing the register tiling again didn't give us much of a benefit and just gave us 10.34 teraflops. Just doing the shared memory tiling is not enough. As mentioned before, bank conflicts can be the hindrance in doing shared memory tiling. So shared memory is basically arranged in banks, usually 32 banks, each being 4 byte wide. So 32 threads from a WOP can access these shared memory banks in parallel. So all the 32 threads can access the 32 banks in parallel. A conflict occurs when two or more threads in the same WOP access different 4 byte words in the same bank. So the threads involved in a bank conflict will need to be serialized, and basically their loads will need to be, or stores need to be processed in separate cycles. So it is known that padding is an effective technique to reduce shared memory bank conflicts. So what we do is like pad the leading dimension of the buffers in shared memory to go from leading dimension to leading dimension plus padding factor. The uses of these shared memory buffers need to be changed in the IR appropriately, but no other change is required apart from this. So seeing this is not quite impressive. It's almost the same performance, around 8.99 teraflops, but there was no much performance gain what we hope to see from padding. So it may so happen that we are trying to optimize some other part of the code while the bottleneck may lie somewhere else. So the bottleneck really lies in the global to shared memory data copy, which is like the slowest part of this thing. So to optimize the global to shared memory data copy, we do two things. The first thing is the vectorization of the copies, and the next thing would be latency hiding. So right now, the copy loops would be copying each thing element by element. Each thread is loading a single element. But what we can do is, as GPUs provide vector instructions, we could use these vector instructions and basically try to speed up our loops. So up to 128-bit is supported on NVIDIA GPUs, and we were able to experiment with different bits, 32, 64, and 128, and got to know that 128-bit version works the best. Now, vectorization utility was again borrowed from MLIR, which is a project here at Polymorphs. This piece of IR shows the scalar copy loop and the vectorized copy loop. So the utility from being a scalar to a to be holding a vector type. The leading dimension of this memref is vectorized, and then what it does is modify the loop steps in a certain manner which ensures correctness. So the step we see here, the step is changed to 8. The third thing it does that it modifies the access functions in a correct manner to ensure that the correctness is not messed up in any way. Seeing what this gives us, and this is like really great, it leads us to 45.9 teraflops of performance. Now we have load store vectorization enabled. We can again investigate to see was padding really giving us any benefit at all. So Just disabling padding, we have everything else enabled, shared memory tiling, register tiling, and load store vectorization. We see that we were almost getting 15 teraflops of improvement with padding in the shared memory buffers. The main key loop of the kernels that we are producing is like this sequential thing. It first loads from global memory, stores to shared memory. All the threads in the thread block are synchronized. Then you do the compute, again synchronize, and this same cycle repeats on. But what you can do is basically pipeline this loop. You can issue the loads a stage earlier, store them to shared memory, and when you do the compute on this data, you can issue the loads for the next iteration in the same iteration of the K loop here. And the loop structure after pipelining would look something like this. That's in the figure below. So after doing all the optimization, this is the skeleton of the IR that is generated. As said before, the outermost two loops will be mapped to GPU.launchOp, which are just basically it will be mapped to the thread blocks. Then we see here the GPU.subgroup MMA load matrix op, which is loading actually the C tile, which is the accumulator tile. It is loaded straight away from the global memory. And the things that are loaded here are passes iter args to the main key loop of matrix multiplication. Outside, we see the copy loops for iteration 0 of the K loop, and inside, we see that the loads for the next iteration have been issued before starting the compute. These loads will be issued, and basically the VOPs will be moving to the next thing, which will be the computation in the main K loop. Then, after the computation and this computation is over, we hope that the loads have been arrived into the registers, and basically you synchronize and store them back into the registers. One iteration, that's the last iteration, has also been stripped out. This is just a computation whose copy has been already done in the main key loop. After this is done, you basically store all the results back to the global memory again. And this is what the kernel looks like after doing all the optimizations that have been mentioned previously. Seeing this gives us around 67.2 teraflops of performance, while QBlast had 68. So it's like really close, and the device peak is 71 teraflops. Now what we can do is like we can try to enable and disable each of the optimization and try to see like what they bring in into this. So just disabling load store vectorization again brings us down by 30 teraflops. So this is because the copies are now much slower. You have low latency hiding enabled, but the copies are actually much slower, so it's not giving any benefit. Again, you take away padding, you come down to 38 teraflops. Again, disabling padding would just slow down the loading of operands from shared memory into the registers. One more thing that you can try to play around with is like you disable load store vectorization and both padding, and basically you are again brought down to 29.2 teraflops. So matrix multiplication till what we have seen looks all good, but what more can we do? So it's a common pattern in deep learning models, like matrix multiplication is followed by some pointwise operations such as ReLU, which may again be followed by something as bias addition. So usually the operations that follow are order of n square operations that have a raw dependency of the on the result of the matrix multiplication. And when you go on to use something such as PyTorch, the following thing happens. Matrix multiplication is done. Then the result of this matrix multiplication is stored to the global memory. Again, it's loaded from the global memory. The pointwise operation is done. And again, it will be stored to the global memory, or some other operation may consume this thing. So this global memory load and store is basically redundant, and it's a high latency operation, and basically it can be totally avoided. So the idea of operator fusion is to do the fusion while the result of the matrix multiplication is available in the register itself. So you avoid the store and load from global memory, do the operation that you have in the registers, and basically move on. This can give us really nice benefits on some small to medium problem sizes, like till 4096. You can see real benefits of operator fusion. But while for larger problem sizes, the computation time itself dominates this time of redundant copy and load. Now we'll be moving on to the evaluation part. Now we have evaluated this whole pipeline on two devices, an Ampere based RTX 3090 Ti and this Turing based RTX 2080. The experimental setup goes like this. All the clocks in the GPUs were set to the boost frequency mentioned in the white paper. And we have right now limited our set to the statically allocated shared memory, which is actually 48 kilobytes in both the devices. The maximum number of registers that were allocated per thread were 255. And the form of matrix multiplication that we consider is C equal to A times A into B plus C. All of the matrices were in row major layout, and we consider square problem sizes ranging from 1024 to 16384 and go on a step of 256. To do all the T-flops calculation, we have just recorded the raw kernel execution time right now. So in general, the results are on par with QBlast for most of the things. Wherever possible, we have used fused implementation. So for example, for ReLU, there was a fused implementation available in QBlast LT, and we have compared our fused kernel with QBlast LT in this case. And where there's not a fused implementation available, we have implemented a custom kernel ourselves, which basically ensures all other performance criteria are met in that kernel as well. So the performance is significantly better in the FP16 accumulation mode on Ampere as compared with QBlast on larger sizes. We think that this might be because the QBlast kernels might not be well tuned for those larger sizes. And upon profiling, we found that they were using like slightly smaller tile sizes in shared memory and basically had more stalls on global memory loads. We also see better performance in the FP32 mode on Ampere than Turing when compared with QBlast. And we think, like again, for Turing, it was the QBlast was slightly better tuned. It almost hit the device peak, while Ampere there was some gap. So we compared our kernels with the absolute device peak, and we saw that we were reaching 90% on Turing and 94% on Ampere. Also, we saw better performance in FP32 mode than the FP16 version on Turing. And we think that the main reason for this thing was in FP16 version, we were not able to try out some large warp tile sizes, which were basically pointed out in a previous work. And those large tile sizes actually led to register spills and basically degraded performance. But those same tile sizes actually worked on Ampere without any register spills, and there we got optimal performance out of those. Yeah, so just moving forward, this is just basically a summary of all the results. There are plots that follow this, but this is just the outline. So seeing this, we almost range from 70 to this 160% of the respective QBlast implementation in matrix multiplication, while for the fused kernels, like we are actually close to the respective library version and basically perform better than the unfused version in most of the cases. Starting with the plots, we'll first see matrix multiplication plots, and then we'll see some plots of matrix multiplication fused with some other operations. So this is really the mixed precision performance on Ampere that we have. It's really close to QBlast, and on some smaller sizes, it actually beats QBlast and basically converges into what QBlast is offering on larger problem sizes. This is mixed precision, and yeah, the device peak is 71 teraflops here. This is for half precision, and it goes like this. QBlast has really inconsistent performance on this. This is QBlast version 11.2, and this might have improved now, but this version actually we performed better on larger problem sizes than 7168, better than QBlast on these larger problem sizes. Looking at the Turing part, this is also something comparable with QBlast. Again, on some smaller problem sizes, we are slightly ahead of QBlast, while on the larger problem sizes, there's some gap. But yeah, in general, this is comparable with QBlast. This is the part where the register spills actually had a negative impact on our performance, and the gap is really some 20 teraflops of gap is present here. Is there some question?
I'm wondering if we know more about how, the reason for the gap with QBlast. What are they doing different? Especially in the last two slides, where
this one
on the following one. where like you have a consistent gap with Kublas.
Yes. So in this one, we found out that the optimal tile sizes that we had, and they were actually leading to some bank conflicts, which were actually larger than the Q plus version here. Yes, so there's one reason for this, and in this one, the particular reason is the register spills. We do not have great control over the register usage, while because we are generating code through MLR, and we really rely on register allocation for this NVIDIA's compiler to do these same configurations. When tried out on Ampere, did not give this much gap. Basically, they ran in the available registers, while on Turing, there were register spills. So this case might be specific just to Turing and is not hurting us on Ampere.
Okay, there's a hand raised if you want to ask a question.
Hello?
Yes,
okay.
we can.
So in terms of the experience of using MLIR in this whole project, like I suppose you had experience using other tools for similar projects. I mean, in terms of MLIR's programmability and user experience, do you have anything to share? Any interesting and significant experiences?
Yes, so basically starting off with like there was actually no support to program the tensor cores in the very first place. So all of the support, that this is like a very preliminary results, and all of the support was added for the first time in MLIR. These ops, WMMA ops were added for the first time, and the things that produce these ops in the affine dialect and some more optimizations and transformations were also introduced for the first time in MLIR. So yeah, there was like a lot of implementation and like good feedback from the community on what was being upstreamed also. So the ops that were introduced to program the tensor cores basically mimic the WMMA API that NVIDIA is providing, and they were upstreamed, and like there was quite a good review on that. And yeah.
Yeah, I think just to add here, perhaps the question was also, how does MLIR compare here with some of the other frameworks that are used to generate this kind of code? So here we've just, we've conducted this exercise just with MLIR, right? But there are other groups that have used, for example, there are other frameworks like Triton, of course, Cutlass, and Navdeep himself did some of this stuff with CUDA, so he can speak about that. But as far as intermediate representations go, we just did this study with MLIR. And the whole goal here was to build a properly layered and modular and reusable compiler infrastructure, right? And so that there's no line of code that is written by hand here. It's all fully automatically generated all the way down. And also just wanted to point out here, for all these different problem sizes here and all the plots, we use the same tile size. There are no different versions yet. There's only a single version, and the same tile sizes prove to be optimal. The thread block, the three tile sizes we use for thread block and three tile sizes we use for the warp, it's the same all the way from 1024 to 16384. But maybe for the smaller sizes, some of the
Is it slightly different? Yeah, from small size. Yes.
So, and in fact, the performance modeling also was quite straightforward, very predictable. We were able to clearly see that the tile size was the one that was maximally fitting in the shared memory. Note that here, we're just using the static part of the shared memory. We're still not using dynamic shared memory. It's still, all of these things fit within 32 kilobytes of the shared memory. So especially on other chips like A100, it's important to use the dynamic part of it, which is much larger. It can go up to 134 kilobytes. So there is, again, more work to be done there. But yeah, I think a lot of this performance was quite predictable, explainable, and which also is good to build analytical models to come up with these parameters.
Yes.
Thank you.
We have another raised hand. Dhruv.
Hi. This is really awesome. I do not know if you have more slides which cover this, but I'll just go ahead and ask. So I'm trying to envision a day where we can like deploy this in like machine learning frameworks or something. So my question would be, how much was the compilation time to actually generate this? Because in modes like eager mode and TensorFlow or something, you do not know the sizes of the matrix multiplications that are going to happen. So you are probably going to do JIT compilation, and however long it takes, even though it's one-time cost and you can cache it, it is still app launch time. So do you have any results or ideas about how long it was taking to go through the entire MLIR structure, LLVM, and NVIDIA's compiler to generate this?
So yeah, this is a good question. Basically, we don't have it here, and I don't want to give an, but we do have a path all the way from TensorFlow tf.matmul to the TF function API that will do JIT code generation and actually generate the code and run it. And it's, I mean, it is under, it's, I believe, a few hundred milliseconds or maybe lower, but
Hmm.
we do have a path, but we don't have the results here to share with, but I can share that with you offline. Yeah.
Yeah, and all of this is available open source, right? That the work you have done.
No, not yet. So I think Navdeep will address that a little later. Like the WMMA ops are all available. They were upstreamed about 2 months ago. So it allows you to target tensor cores and run. But some of the other passes, and we're going to talk about that plan. We're planning to do it sort of starting from the lower layers and basically upstream it in that direction, right? But the WMMA ops are there, so which means you can actually write something that will run on the tensor cores correctly. Right? And a lot of the infrastructure is already there, like the tiling and other utilities, but the WMA mapping and some other things are still missing, right? Yeah.
Sounds good. Few hundred milliseconds sounds really great. Thank you.
We had a question on the chat from Benoit, who asked, in NN applications, almost all the sizes that matter are smaller than the 124, 1024 you measured. So have you benchmarked like those smaller sizes?
We've not benchmarked it for smaller sizes, smaller than 34, but we believe there would be reasonable performance in those sizes as well. But these are the larger sizes that this particular thing, range of problem sizes, is what has been evaluated in some previous works. Plus, some of these sizes are really what are being used in BERT. So but like there will be really large matrices that will be ranging from 1024 to 4096 and maybe even larger than that. Basically it depends on the batch size and the sequence size and other things that you choose, but yeah, this is a good estimate of the problem sizes that could be available in the future and which are presently available. There may be some special problem sizes which may be smaller than 1024, which may require some further tuning.
Yeah, so you mentioned batch size, so I assume you're talking about training, whereas there are cases of inference, and in inference you don't have the batch size, which makes the problem size smaller.
Yes, in training, yes. There's some batch size and then there's sequence size, I guess.
Yeah. And so the question was about inference then, because in
Oh, okay.
inference you may have smaller problem sizes. And I think the
Okay.
question was like, how do you think your work would perform, or are there different challenges maybe when you go to smaller problem size?
Okay, I think the performance would be reasonable.
Yeah, we should.
Until,
I think. Yeah, we don't have those results here, but this code actually works all the way down to 16 cross 16 matrices. You will. We are able to do it. That's the smallest thing we can run, right, without padding. 16 cross 60 because it was a WMA API. That's what it gives us. But perhaps we should. Yeah, if you could go to the Ampere plot and look at the performance trend near 1024, right? Again, even here it's close, right? But we really, yeah, we should also include maybe in a future, perhaps in an updated revision. This is going to be available in an archive report, so we should also look at those sizes. There, perhaps we may have to choose smaller tile sizes. Sometimes the tile sizes, yeah, will have to be smaller because the problem size itself becomes smaller. But yeah, that's where we perhaps might get more improvement. But I think let's go to the fusion results, and we'll come back to this in the interest of time. Right, so there are some trends there that might be useful.
okay. Yes. So moving on, some of the results from the fusion side. This is again mixed precision fusion with ReLU on Ampere, and the comparison here is with Q plus LT. So the thing to note here is that both QBLAS and R kernels, they do the fusion at no extra cost. You just have the outputs in the registers, you apply the ReLU, you apply the cutoff, and then basically store it back to the global memory. So this plot is basically the same as what we had with plain mixed precision Matmul, excluding ReLU. Next plot is like with a constant add. So this was particularly chosen just to show if there's some operation that does not has a library implementation, what kind of gains can you get on those things. So here MLIR clearly beats QBLAS plus a custom kernel implementation like across the whole problem range. And the gains are really significant on smaller problem sizes up to 4608 or 5120, even like that. On the larger problem sizes, again, the kernel execution time starts to dominate the cost of this redundant loads and stores from global memory, and the performance benefits are not that much. And yeah, just pointing out, so maybe even for smaller sizes, less than 1024, the gains that you see by doing operator fusion, maybe even more. Just yes. Again, this a slightly different fusion of Matmul with matrix addition, and there was a similar pattern that we saw in BERT, where basically batch matrix multiplication is followed by the addition of an attention mask. So this is a slightly simplified scenario. This is not a batch matrix multiplication. It's matrix multiplication, but again, it's followed by an addition, which was the case in BERT as well. So in this case, now the whole matrix has to be loaded from global memory in the case of the non-fused version, which is QBLAS plus this custom kernel. So the gains actually increase from this constant addition, where the constant was assumed to be in the registers, while here the whole matrix that is being added is to be loaded from the global memory itself. As you go on adding more and more ops that can be fused, you will see the performance over the non-fused versions go on increasing. And here matrix addition was followed by a ReLU, which again involved two redundant load stores from global memory and application of ReLU. The same thing, the fusion on the output side, the fusion can be done on the input side as well. So this plot really shows the C matrix being produced by a ReLU operation, which was in turn used into the matrix multiplication. Here also the same trend is followed on like small to medium problem sizes, and the gains are significant. And this is basically the same trend as we had for output fusion with ReLU. Yeah. So coming to the end, these are the things. So basically, we put together this automatic code generation pipeline that appears to be really promising, and there's a lot more work to do, but these initial results look nice. And these basic operations to program the tensor cores were basically contributed upstream. Yeah. Was there a question?
No.
Okay. Sorry. Yes, we plan to work and contribute other layers of this pipeline, starting from the most layer ones, like this most lower part of this pipeline. These ops were already contributed, and we wish to contribute the other parts as well to the upstream. We also want to discuss how to generalize the mapping of these SCF loops to GPU with WOP level support. So this mapping to the WOPs is actually absent in MLIR, and we have some custom thing going on here, which actually works for matrix multiplication, and would even work for some other problems which can be basically encoded to matrix multiplication. But coming up with a general thing which maps some parallel loops or sequential loops in a given IR to the GPU would be really great. We generate the WMMA operations in the affine dialect itself, and we would also like to contribute this mapping back to the upstream, and the generalization of operator fusion to handle a variety of fusion scenarios, like more number of ops or basically in the input, not with C matrix, with A and B matrices would also be a good thing. And the ultimate goal is to build a modular and reusable code generation pipeline, basically with these building blocks, which can go just beyond them, maybe used in other things like convolution, something like that as well. Yeah. So Yes, that was it. Thank you. We can come back to more questions and discuss other things as well.
Thanks a lot for the talk, Navdeep, and congrats for the results. That's very impressive. There was a question on the chat. Prashant, you may want to repeat it out loud.
Yeah, sure. I think firstly, Navdeep and Uday, I think this is really cool work because generating the efficient code for tensor cores is something that hasn't been really deeply explored, and also getting performance closer to the kublas is very interesting. I think my main question is that oftentimes in the deep learning models, we encounter the irregular matrices, meaning that the values of m and k may not be the same always. In fact, in extreme cases, we might encounter tall, skinny matrices. So the question is, so far, do you have any experiences on the performance of generated codes on such irregular matrices?
No, on very large tall and skinny matrices, we have not tried this out yet. There were some previous works which pointed out like a totally different strategy is needed for those kind of things. So suppose the k dimension is really large while m and n are small, a different set of optimizations is needed there. Basically, you can do a parallel reduction in that k dimension. That is still not present here, but can be incorporated as well. While going to other queue sizes where m is really large and k is really small, some other type of optimizations would be necessary, which are not really present. But rectangular problem sizes, where like these m and k dimensions are large, somewhere around 1024 or maybe 512 or larger than that, it would be worth experimenting, but there we can see comparable results to this. Yeah.
I see. Thank you.
Yes.
Thomas, you have your hand raised.
Right. Yeah. I wanted to ask, do you have any other optimization in mind you're planning to try, or some stuff you've tried that didn't really give much performance? One thing I was mostly like thinking about, I think Navdeep mentioned it in Catlas, right? There is this epilogue that potentially reshuffles the data in shared memory to get better global memory accesses. So those kind of layout changes, have you considered those? Have you tried anything out, and are you planning to try anything?
Yes. So basically, that rearrangement that they do is, yeah, you're correct. It's for efficient accesses to the global memory. It may so happen that the results in the registers are not in the same layout as it is expected in the output matrix. So basically, they store it back to the shared memory in the expected output, and they perform the stores back there in such a way that vectorized and coalesced accesses are guaranteed. Right now, what we are doing is we are just using the WMMA intrinsics to store that back. The technicality here is that we are basically limited here. Currently, we are limited here by the static shared memory size that is available to us. That turns out to be 48 kilobytes on most of the devices. So the first thing that we are planning to do is basically add support for dynamic allocation in MLIR to go beyond those things, and then we may be able to subsequently try out larger tile sizes and basically more stages of pipeline that Cutlass has, maybe 3, 4, 5 stages of pipeline in the main K loop that Cutlass has by doing that. Yeah, we will be able to enable all those optimizations in the near future.
Okay, that's cool. And have you considered pre-tiling the global memory itself?
Pre-tiling, I'm not actually clear with pre-tiling.
So basically, trying to rearrange the data so that the tiles you're loading into your MMA units, you could like pre-process the input data so that they're already contiguous. So then you have like much better global memory accesses on the loads.
Oh, okay. So using the WME intrinsic just to load from the global memory, actually, you need not do that.
No, I think what
correct. Yeah. Sorry.
Yeah.
I think Toma is mentioning that you can basically use a tile layout in global memory, and would that improve accesses either for the LHS or basically even the loads from the global to shared, right, from the LHS and RHS?
Yes, you would need then a custom loader that would be loading things from global to shared memory, which would incorporate this tile layout and ensure other things like vectorized accesses and coalescing in the global memory. But yeah, that is worth considering. Yes.
Yeah, we have not considered that. So right now it's
Okay.
just row major, assuming that whoever is producing the input matrices for the Matmul is producing them in the row major layout. Right? Yeah.
Okay, interesting. And anything else then you have up your sleeve, like coming up in the future? Just wondering. Like other than layouts or like other optimizations.
Well, I think as others rightly pointed out, we should be also looking at the some of the common sizes. Use smaller sizes, the tall and skinny matrices. But the lower hanging fruit right now is, as Navdeep mentioned, we wanted to basically make use of the dynamic memory also, so that we have larger tiles, right? And our goal is really not just Matmul, but here it's all about things that are not captured by libraries, and that do not compose well by just using the libraries, but we can do a fully automatic code generation and exploit register reuse across different ops. So that's going to be the goal, and we are sort of just encouraging that for the good sizes, right? We're getting close to cube loss, and the goal is to be within 10-15%, so that you're not far away when you start doing fusion. Yeah.
Great, thanks.
All right, and we are right on time to close the session, I think. Thanks again for Uday and Navdeep for this talk and for the work. I'm looking forward for upstreaming this and for the future developments around that. And thanks everyone for attending, and see you next time.
Yes. Thank you, everyone.
Thank you.